So if we continue our discussion of this stopper being whirled around in this conical type shape, this could be the same as a banked curve. So maybe you've been around a curve before and the road is not flat, but it's got an angle to it. So it's kind of this banked curve type thing. If you watch NASCAR or something like that, the curves are banked so the cars don't slide down. So the car would actually be at some angle like that, but going so fast that it needs the curve to stay in there. Or even an airplane. So when you take off in an airplane, so here our airplane, there we go, there we go. So here's the airplane, maybe it's got a little wing in the back there, and that airplane is banking. So probably you've had the experience of when you go up in an airplane, the airplane will bank back and turn around, or maybe when you are coming in for a landing, if there's a banked type, it's turning, or maybe it's circling the airport because of weather or landing times and things like that. So there's a lot of times when we might have an object moving in a circle, but it's not flat, okay? And so all those are cases that are similar. It's just a different force acting on the object to keep it moving in the circle. So the tension force here would be like the normal force here, which would be like a lift force or some sort of buoyant force or something like that, because of the shape of the airplane wings as it goes around. So I'm going to sum up the forces for the stopper and use tension, but know that if it were a banked curve, you could just change it to the normal force. If it were a airplane, it would be some lift force that was holding it in that circle. So we would have a center of the circle here, we'd have a center of the circle there, center of the circle here. So if I draw my free body diagram, we'll have the stopper and the tension force and the gravitational force, and a lot of times we have the angle to the vertical for the tension force. Yeah, the horizontal angle, you would just flip your sine and cosine. So when I sum the forces in the x direction, there is only one force in the x direction, and it's pointing towards the center of the circular path. And so it must be equal to MAC. That force would be FT, but opposite, so sine theta would equal MAC. And then, but in the y direction, the sum of the forces is balanced because the stopper's not rising or falling, the airplane's not rising or falling, the car is not sinking into the ground or floating off of the ground. In all those cases would be similar. So then I had FT cos theta because it would be adjacent to the angle, minus F sub G is equal to 0. So that's basically how to sum up the forces. Now, if we look at this a little bit closer, the tension force would be equal, nope, not equal, but the tension force times the sine theta would be equal to mv squared over r, doing a substitution for AC, and then ft times the cosine of theta would be equal to mg. Add f sub g to both sides, make that substitution. Now, just like in math, you can add and subtract equations from each other to eliminate variables. You can multiply both equations by the same number, things like that. We can also divide equations by each other. And it's just a fast little math trick there. So tension and tension would cancel out. What's sine theta divided by cosine theta? Tan theta. Oh my goodness, the mass doesn't matter. And so then you're left with v squared over rg. Therefore, the speed of the thing that's moving around in this circular motion would be the square root of rg tan theta. All right, let's look at another example. So we've probably gone over a hill in a car. We may have even gone into like a valley or a little dip in the road. You may, so this would be like a hill, and this would be like a dip. And then maybe you've even ridden this fun thing like a Ferris wheel. So here's my drawing of a Ferris wheel. And when you're riding a Ferris wheel, you sit upright both at the top and the bottom. And when you're riding in a car over a hill, usually you're sitting upright, unless you're doing something crazy in the car, upright in both places. So what I want you to see is that at the top of the hill, it's the same sort of scenario as if you were at the top of the Ferris wheel. And likewise, at the bottom of the hill or in a dip, it's like being at the bottom of the Ferris wheel. So let's look at the top and the bottom. They're interesting. So the forces acting on an object. Now, the Ferris wheel, it's pretty easy to see that a Ferris wheel has a radius. But what about the hill? The curve of the hill also has this tangent circle, which would have a radius. And maybe even the dip has kind of like this tangent circle to it. So it would also have a radius. Okay? So at the top, the free body diagram would look like, what forces are acting on you when you're sitting in a seat? Definitely a normal force, straight up. What else? A gravitational force, absolutely. And that's all. And the center of the circle is below you. So either you're sitting at the top of the hill or you're at the top of the Ferris wheel, but the center is below you. And if we let, now this is really important, you have to pick a coordinate system. And it is to your best advantage if you let towards the center be the positive direction and away from the center be the negative direction. So that when you sum the forces, and when I sum the forces in the y direction, they have to be unbalanced. If they're unbalanced, then there's an acceleration. And if there's an acceleration and a radius, then it could be moving in a circle. So if those two forces, if the normal force and the gravitational force are equivalent, the object's not moving in a circle because there's no acceleration. Okay? So they have to be unbalanced in order for it to move in a circle. So if I use the rule that towards the center is positive, then when I sum the forces, Fg minus force normal would equal MAC. Okay? That means that the net force would be positive, and the net force should be pointing towards the center, and towards the center is positive, so all my signs are in agreement. If I didn't make towards the center positive, and I let it be negative because it's below me, then I would have to make this a minus MAC. And I find that students make more mistakes when you change up the coordinate system for every place that you're at. Sometimes it's positive MAC and sometimes it's negative MAC. So I think you're better off if you let towards the center be the positive direction and away from the center be the negative direction. Now, that means I could find the normal force. The normal force is your weight, or your apparent weight is what I really should say. So wouldn't this be F sub G, your actual weight, minus some MAC equal to force normal? How do you feel at the top of a hill You feel lighter, maybe weightless if you come all the way off the seat. So this normal force here is your apparent weight. Remember, your mass doesn't change, but your weight can change depending on what planet you're on and things like that. So your apparent weight can be different. And that's what makes riding rides with hills and dips and a Ferris wheel that goes around and around. That's what makes it fun, is it makes you feel different. Right now, you're just sitting here. You have no net force acting on you, causing you to feel funny. It's the same force that acts on you all the time. You're just feeling normal. That was a joke, because that's what you feel is the normal force. Yeah. All right, anyway. So you feel light at the top. Now let's look at the bottom, the dip or the bottom of the Ferris wheel. If we draw a free body diagram, when we're sitting at the bottom of the Ferris wheel or in the dip on the car, or on the hill in the car, there's still a normal force acting on you because you're still sitting in a seat, and there's still a gravitational force acting on you because you're still on the earth. If you're at the bottom of the hill, then the center is above you. If you're at the bottom of the Ferris wheel, the center is above you. And we let towards the center be positive. So if we sum up our forces in the y direction, they must be unbalanced if it's going to move in a circle. If they're balanced, there's no acceleration, thus no circular motion. So in this case, the normal force is positive, the weight force is negative, and then AC is positive because the net force is towards the center. So then if you go in and you're like, oh, well, let's find the normal force here, or how do I feel my apparent weight? Well, it would be your gravitational force plus this MAC. How do you feel at the bottom in the dip, the bottom of the first hill on a roller coaster? Heavy. Don't you just almost feel like you're just being squished into the seat? It's hard to hold your hands up in the air. Okay. So this is still our apparent weight. And this addition shows me that I feel heavy. And that's why riding those rides is thrilling, because it makes you feel different at different points in time. Now there's another one. So let's look at the loop. How about that? So I always think about the Mindbender. It was the first roller coaster I ever rode that went upside down. Six Flags. So when you're at the bottom, it's like you're sitting at the bottom of a Ferris wheel or the bottom of any other hill. But when you're at the top, how are you oriented? You are upside down. Whee! But we don't fall out because we're moving. That's right. We're moving tangent to the curve at all times. So no matter where we are, we're about to run into the track. All right. So when you are going through the loop here, so this is the velocity, I'll label that. If we were to draw the free body diagram of all the forces acting on you when you are upside down, and you're sitting on a seat and you're upside down, what force or forces would be acting on you? And they would both be down. The gravitational force is down because it's directed towards the center of the earth every single time. And the normal force is from the seat onto your rump, so that would also be down. Holy cow. So how do we stay up? We stay up because we're always moving tangent to the curve. The center is below us. If you let towards the center be positive, then when you sum the forces in the y direction, they must be unbalanced, otherwise you're not moving in a circle. But your normal force and the weight are both pointing towards the center. And usually you feel heavy as you go through them because you're going pretty fast. Now, we have these little Hot Wheels loop-de-loop cars, loop-de-loop track. You've probably seen it before. I have them in the back there. So sometimes, though, we can go through a loop and just barely make it through the loop. So let's look at a minimum case where we just barely make it through the loop. So if you're barely going to make it through the loop, that means that at the top, the tires of your little car come off the track. They're not touching. So for the moment that you're exactly upside down, you're not touching the track, but you're going this way. So in the next moment, you're going to hit the track and it's going to pull you back around. Because you're always moving tangent to the curve. Move tangent to the curve here, it pushes you around. Tangent to the curve, it's going to push you around. Tangent to the curve, push you around. Now, if you're lost contact right here for just the moment that we're upside down, then the normal force would be equal to what? 0, because we are not touching the track anymore. And then the free body diagram would have just the gravitational force acting on the object, with the center still below. Definitely forces are unbalanced here. The sum of the forces would be equal to MA, and if it's moving in a circle, better be MAC. So the gravitational force would equal MAC, but the gravitational force is the weight of the object, which is the mass times the gravitational field constant. And the centripetal acceleration would be v squared over r. So what doesn't matter? The mass. That's why there's not a weight requirement for riding loop-de-loop rides. The mass doesn't matter.
Why is there a height requirement?
Because some accelerations can cause your heart to do funny things. Okay, so then if I rearrange this, what do I get? I get the velocity is the square root of rg, and that's a very special equation. We even give it a special name. We call it the critical speed. And it is the minimum speed to make it through the top of the loop. So any faster is fine. And most of the rides you've ever ridden on, you're going way faster than needed. That's why you feel that crazy acceleration that makes you maybe feel real sick. Just thinking about it kind of makes me feel sick. Anyway, so, but then there's an alternate to this. What if instead of going upside down, you're going over a hill? Have you ever seen those movies with a car chase and they go over a hill? What happens to the car at the top of the hill? Yeah, it's like projected over. Sometimes it's like, whee, and the car goes flying over there because it's moving tangent to the circle, and if it's going fast enough, it'll actually project itself because it's moving so fast, it won't stay in the circle. So the alternate to this is that if you're going over a hill in a car, and the screen machine makes me feel this way, is your car momentarily leaves the top of the ride. Oh, that is a pretty car. You're jealous. Okay. So anyway, whatever. Okay. So still the normal force is 0. So we are for the moment weightless. So this is when you feel weightless. So then when you draw the forces acting on this car, there would be just the gravitational force pointing towards the center. So that when you sum the forces in the y direction, they're definitely unbalanced. The gravitational force would be equal to MAC. The gravitational force is the mass of the object times the gravitational field constant, which would be mv squared over r. So do you see we're getting the same equation for the velocity, but this time it's not a minimum speed, but it's the maximum speed to stay on the hill. So if I design a roller coaster, it's fun for my roller coaster riders to feel weightless. So I'm going to devise my chair, my restraints, so that it holds them in. And then when they go over the hill, so come up whee, a little bit out of your seat. Nope. Do you ever? Nope. Okay. Yeah, you come out of your seat a little bit on the screen machine every time. I ride it with my kid, and I'm like, oh my gosh, don't fall out. But it's designed with the seatbelt and the restraints so you don't come out of it completely, but you get that fun feeling of weightlessness. There are lots of different places, maybe in the road, if you've been driving around, or you go up over a little, like, whoop, in the road, and that just means that place right there, you were going fast enough that you just kind of came out of your seat. Your normal force wasn't quite zero, but you were approaching root RG.